Good afternoon, everybody. Welcome to the Mary Jackson named lecture. My name is David Chin. I'm the president of the society. I'm sorry I can't be with you today. I'll do the introduction, then I've got to go to another society event. I think I'm triple booked today. But welcome to this event, which has been taking place with our colleagues in the AIAA D&I group. In terms of logistics, if I've got it right, please keep your microphones off. There is a Q&A button and questions will be taken at the end. In terms of a bit of background, Mary Jackson was the first black aerospace engineer in NASA in 1958, if I've got the figures right. And this lecture was started jointly in 2021. I think I've introduced the last couple, which is a great honour. The Aeronautical Society is committed to having an inclusive culture, and this is part of that workflow. Workflow's an awful word, but you know what I mean. To our speaker, it's a great honour to introduce Gaitee Hussain. I hope I pronounced that correctly. Head of Science Engagement and Oversight at ESA. And she's got a great background. I saw when we were doing the introduction, both the background to the screen and a CV, if I can link things together. She's an accomplished astronomer, BSc in physics and astronomy, PhD in astronomy from St Andrews, a beautiful university, if anybody wants to go up there. Fellow at the Smithsonian, astronomer at the European Southern Observatory, and visiting chair at IRAP, which I've never heard of in Toulouse, but it sounds like I've got a few things to follow up there and perhaps a few visits. So I will now hand over to our speaker and have a great evening. Thanks very much.
Thank you so much for the introduction, and thank you even more for the invitation to speak today. So over the next 40 minutes or so, I'm going to take you through recent advances that are happening in terms of space science research that the European Space Agency is at the forefront of. But I also want to highlight throughout the talk the importance of the many communities that are involved in contributing to the success of our missions. And of course, that also requires constantly thinking about inclusion and making sure that we have all talents on deck as we build, implement, and operate our missions. So I will begin my presentation now. And 1 second, try to share the right screen. Give me 1 minute. So here we are. So I hope that you can now see the screen, but let me know if there's any problems. And I just wanted to, before I start, of course, say a few words about Mary Jackson. So I think the thing that I think about a lot in my career is that I was extremely influenced by seeing people of backgrounds that I could relate to in the generations ahead of me, blazing a trail in areas of physics, astronomy, and space science. I think what's truly remarkable about Mary Jackson and her generation is that they were the first, and the amount of resilience, toughness, and self-belief that it takes to survive that, I think, is absolutely remarkable. I'll be coming back to some thoughts about Mary Jackson later on in the talk, but I do wonder where we'd be today without, in terms of inclusion, in terms of having diverse talented inputs in our communities without figures like Mary Jackson. So you already heard a little bit about my background, but I do think it's worth highlighting it for a number of reasons. So I started out in St Andrews. I did my PhD there in astronomy. And I got an independent research fellowship at the Harvard-Smithsonian Center for Astrophysics, followed by a fellowship at ESTEC in the Netherlands, where I am back now, 20 years later. I was back in St Andrews briefly as a postdoc. And while I worked at the European Southern Observatory as a staff astronomer, I held a number of roles, including a visiting position at ERAP, which is this research institute in Toulouse, which I absolutely recommend you check out. So I fully endorse the introduction on that. And as of 2020, I have taken up this role at the European Space Agency in the Science Directorate, where I am responsible, or rather I head a unit that is responsible for maximizing the scientific output of the missions that are led out of the Science Directorate. So we work very closely with communities from across all of our member states and beyond in order to deliver the most relevant cutting edge science that Europe can deliver these days. My background is in research. It is in looking into stellar activity for solar type stars and using our understanding of the stellar activity, their variability, in order to be able to detect planets around other systems other than our solar system. And so I'm extremely passionate about data and observing and getting your hands dirty with actual data and seeing what you can make of it. My trajectory put out onto a map looks a lot like this, and this is very typical for a trajectory of astronomers and a lot of space scientists as well. So you often ricochet around a few different countries, sometimes a few continents if you're lucky, and you gain a lot of experience and a lot, particularly of multicultural experience along the way. And I do believe that's really important in the way that you then subsequently can look at how to ensure resilience in the communities that you try to strengthen related to your missions. Now, before I get into our science missions and some highlights from our science missions, I just wanted to remind you about the European Space Agency itself. So the European Space Agency is made up of 23 member states. That also includes one long-standing cooperating state, which is Canada, as well as 4 associate members. It was formed almost exactly 50 years ago out of 2 separate organizations that essentially merged together. Essentially, they were based around launchers and doing space research, and that was merged together in order to form the European Space Agency. It is committed to the peaceful exploration and use of space for the benefit of people, society, and our planet. And it is absolutely at the forefront of advancing scientific and industrial interests in space. You can broadly divide the work of ESA into 4 main pillars. In red, you have what we call science and exploration. That's where the Science Directorate lives, but also where our colleagues in the human and robotic exploration live. And so that is where the astronauts are. It's where they're planning future rovers and missions to the moon and Mars. And in yellow, you can see the pillar that is essentially entitled Enabling and Support. And so these include obviously transportation, so launchers, as well as operations. So radio stations, satellites through which we can downlink, uplink commands, really important for actually operating our spacecraft once they're launched. And of course, technology development, which is continuous. Another pillar is the 3rd pillar out of 4 is applications, and these there's a big component of it focused on Earth observation and providing satellite imagery which allows rapid response for various different applications on Earth. Related to that, of course, we also have navigation satellites. We also are working on secure communications and commercialization in order to ensure Europe can stay at the forefront of this vastly expanding sector. And last but certainly not least, and underpinning all of our work, is space safety and security. And making sure, especially at the moment, the policy that we're implementing for all of our satellites that we are sending up, but also our older ones, is making sure that we can deorbit them safely and we're not leaving a legacy of debris. in space. Now, going on to the Science Directorate in particular, we are working hard to empower Europe to lead in space science. And this is across a wide range of scientific areas. It can broadly be described as heliophysics, planetary science, astronomy, and fundamental physics. Now, of course, these are extremely broad umbrella terms, and they catch a lot of different techniques, methodologies, backgrounds, and almost by nature, they are interdisciplinary. Working in space science is an interdisciplinary activity. The entire suite of missions can be divided up into two separate families, effectively. We have the solar system explorers and we have the cosmic explorers. The solar system explorers are summarized in this cute little cartoon here. Along the top, you can see the missions that are either being are actually being developed, and in fact Proba 3 was very recently launched. In the middle, you can see the missions that are currently in operation. So they are in various parts of our solar system and sending back data as we speak. And along the bottom, you can see the missions that are now in legacy phase. So they have already delivered their data into our archives where they will be available for future generations of astronomers, space scientists, and planetary scientists to benefit from. But they are now, the satellites themselves are now resting in various parts of our solar system, or they've been deorbited. And oh yeah, so sorry, I just wanted to go back to that quickly. So we recently launched JUICE in 2023, and that is undergoing its cruise phase. It's heading towards Jupiter, but it's already conducting really interesting science while it heads towards the Jupiter system. We also have the Bepi-Colombo mission, which is heading towards Mercury and is due for orbit insertion next year. But it already is also conducting really interesting science along the way. And the other missions are in regular operations. The other suite of satellites we have are called the Cosmic Explorers. And again, along the top, you can see the missions that are currently in development, and the ones that are active and relatively new are highlighted by the circles shown here. These are Euclid, CRISM, and Einstein Probe. Euclid is an explorer of the dark universe. It has already embarked on a 6-year survey in which it's going to map the last 10 billion years of cosmic history of our universe in order to understand the nature of dark matter and dark energy, namely 95% of what makes up our universe itself. CRISM and Einstein Probe are high energy satellites, and CRISM is a partner mission with Japan, and Einstein Probe is a mission that is led by the Chinese. Recent launches were in 2023. The most recent launches were in 2023, and they included JUICE, which was launched on 14th April 2023 from Kourou in French Guiana, and Euclid, which was launched from Cape Canaveral on a SpaceX Falcon 9 on the 1st of July 2023. And it was, I was fortunate enough to be able to witness the Euclid launch in any case, and it was absolutely spectacular, my first launch ever. Now, Euclid, in a short year and a half, has already been producing spectacular images and data that it has made available for people to benefit from around the world. And here you can see a mosaic made of 6 images that were sets of images that were taken and built from Euclid observations based on a relatively short range of time. And you can see that it managed to capture a wide variety of objects, ranging from a spiral galaxy, IC342, which is very much analogous to our own Milky Way. In the middle, you can see the iconic Horsehead Nebula, which is a nearby star-forming region. And you can see Euclid's very wide field of view allows us to capture not just the Horsehead Nebula itself, but the entire region around it. And And on the right, you can see NGC 6397, which is a globular cluster, which is a very dense concentration of stars close to Earth. It's about 7,800 light years away. And the amount of detail that you can get with Euclid is astonishing because you can capture the entire globular cluster. But if you keep zooming in further and further, you actually manage to resolve individual stars, and you can gather a lot of information that we never managed to from this actually formerly well-studied cluster. On the bottom left, you can see an irregular galaxy. And on the right, on the bottom right, you can see the Perseus cluster. And this is this is basically an image showing over 1,000 galaxies belonging to this cluster of galaxies. And there are more than 100,000 galaxies further away in the background. And just to showcase um, the astonishing capabilities of Euclid alongside other satellites that we work with every day. There was this beautiful image release that was made by our teams showcasing the Euclid image of the Horsehead Nebula, which I just showed you, and a comparison with an updated image using the Hubble Space Telescope using its infrared instrument, and a comparison with what you get with the James Webb Space Telescope in the infrared. And you can see the exquisite level of detail recovered by JWST is extremely complementary to the information that we're getting from Euclid and Hubble. So living in a time that all three of these seminal satellites are working together is extremely valuable and has a lot of potential. In October last year, we had a release. I'm not sure you're going to hear the music, but I will play the video, which shows what Euclid is actually designed to do. So as I mentioned, Euclid is a dark universe explorer. And its goal is to map literally over 10 billion galaxies and their properties in order to measure properties of dark matter, and with a separate set of data to measure how matter has clustered over cosmic time in order to understand the nature of dark energy. And together they make up 95% of the universe. In this sneak preview of what the survey will have to offer, this is just 1% of the Euclid survey. And it was an image that was released and turned into a movie towards the end of last year. And you can see that we start off with a picture taken by another satellite by Gaia. And then it gets superimposed with a picture from another seminal ESA satellite, from the Planck satellite. And then you will begin to zoom into the region that Euclid observed, and it just keeps zooming in. And you can see the exquisite amount of detail that Euclid is going to enable cosmologists to recover. So here you can see an image taken from our Gaia satellite of our galaxy. This is superimposed with an image from the Planck mission. And this is the area that Euclid will observe in its survey. This is the region that was released in October. And this one patch of sky is it covers more than 500 times the area of the full moon. And you can see, you can keep on zooming in. And you'll see more and more galaxies and more detail related to those galaxies. And in many of those galaxies, you can even resolve individual stars. Now you're zoomed in by 150 times, as the caption says, and you can just see the exquisite amount of detail. This one piece of sky that Euclid has mapped already contains over 100 million sources. It's only a fraction of what Euclid will obtain over the next following 5 years. It's only 1 year of the survey has been completed. So, moving on, sorry. Let's try that one. Yes. Now, the thing I wanted to emphasize about Euclid is it requires all of Europe essentially pulling together. So you can see major European partners that have contributed to Euclid outlined here, and you can see the specific institutes and space agencies that were involved in bringing this mission together, working, of course, very closely with the European Space Agency. That was essentially the industrial part. It also involved over 300 academic institutions, 21 countries within Europe and outside, and over 3,500 people. We actually have in the Euclid Scientific Consortium over 3,500 people spanning a wide range of ESA's member states and the US. And altogether, there are 9 different processing data centers simply because the amount of volume that's being downloaded is so enormous and it needs to be processed in a distributed fashion. And so this massive effort requires bringing together huge communities, and again with very disparate and diverse talents. Going back to one of our partner missions, which I already touched on, is the James Webb Space Telescope. And there's a spectacular image that was recently released of this young stellar object, which is still forming inside this cocoon of gas and dust that you can see. What you can see on the left are different views of this young stellar object in different wavelengths. So on the top left, you can see what HST recovers. On the top right, you can see the James Webb Space Telescope image taken at near-infrared wavelengths. If you look at longer wavelengths at the mid-infrared, you can see the view becomes quite different, and it really emphasizes this jet that's coming up perpendicularly from the stellar object itself. In the bottom right, you can see this orange dashed line, essentially, which is data taken from a ground-based facility called ALMA. And this is a millimeter view, a millimeter wavelength view of the same object. Bringing together these different views, you can produce this false color image, which highlights different features. So here what you're seeing, if I can guide you through the combined picture that you're seeing on the right, you're seeing this energetic jet that's being released from this object that's forming inside. You can't see the object itself, but you can see disk winds emanating from the disk surrounding the stellar object itself. And in the middle, you can see it's shrouded by this thick disk that we're basically seeing completely edge on. So these spectacular images that we're getting from the James Webb Space Telescope combined with complementary facilities, again, are bringing together huge communities of scientists to begin to answer fundamental questions about star and planet formation. I wanted to spend a few words telling you about the Gaia satellite, which is it's our seminal satellite at the moment. It is by far producing the most publications and the most knowledge, generating the most knowledge in the astronomical world as of the last few years. So this picture that you see is a picture essentially of our Milky Way. And what you're seeing here is not just a picture that's been made by an image that's been taken, every point in this image is a star that has been, whose position and proper motion, so its velocity essentially, has been measured in detail. In just a few years, Gaia data has been used in more than 4,000 scientific refereed publications. And it provides different views onto our own galaxy. And here is a subset of some of the data it's managed to produce. And here we're just focusing on a small part of the data of the different views that Gaia has provided of our own galaxy. So in the top row, you can see a map of the amount of dust in our galaxy measured. It's called extinction. In the second row, you can see information about the chemical properties of evolved stars distributed across our galaxy. In the third row, you can see again where dust is, but measured this time in individual stars. In the row below that, where you have these red band streaking across the center of the image, it's a measurement of what we call diffuse interstellar bands. It's showing you where interstellar bands are located in our Milky Way. The image below that shows velocities measured for individual stars. And you can see that there's this interesting pattern where you have stars that are coming towards us, and that's why it's darker. And stars that are going away from us are sort of brighter. And you can see that there's a broad, it traces out the broad motion of the galaxy as it rotates, but there's also structure within that, related to the different spiral arms of our galaxy itself. And so you can see we have all of these different views of the galaxy provided by one satellite. Now, all of this information is for individual stars as well as the interstellar medium around them, so the dust properties around each of the stars. And this is leading to massive advances in many different areas of astronomy. One example of some really important results that Gaia managed to extract, the Gaia data has managed to uncover, are that we have found a whole new family of black holes. So in the past, we are adept at finding black holes via energetic phenomena that are happening around them. So essentially, they often have accretion disks, which means that they can generate high energy radiation in X-rays and gamma rays, and UV and X-rays. Gaia, through the motion of stars orbiting around black holes, has found a new family of black holes, which are much lower masses. So they're in a range of between 9 to 10 solar masses, which is Gaia, what's called Gaia Black Hole 1 and Gaia Black Hole 2. Astronomers are not the most imaginative in terms of how we name things, but Gaia Black Hole 3 is a particularly unusual beast in that it appears to be 33 solar masses. So these are objects that we've long expected exist, but Gaia is actually finally allowing us to uncover them and understand the pathways through which what we call intermediate mass black holes, which is what these are, that they're solar mass, many solar mass black hole, many solar masses of black holes, if that makes sense. So they have masses of more than 10 times solar masses. They're called intermediate mass black holes. And so finding these black holes is extremely important for understanding the pathways through which black holes form. Another really neat thing is that Gaia not only managed to track the motions and the properties of stars across our entire galaxy and beyond, but it's also been an incredibly successful asteroid tracker. And there's this really great movie that's been generated from data that has been extracted from Gaia, showcasing the orbits of over 156,000 asteroids in our solar system. And that's shown by this movie here. So here you can see beyond Neptune, there's about 24 orbits, 24 trans-Neptunian objects that were found. Zooming in, you can see big these are main belt asteroids, where the bulk of the asteroids in our solar system are, and they're found between Mars and Jupiter. Moving inwards, we then reach a population that is most likely to cross Earth's orbit, and that you will see shortly. And the reason that they get while the main population of asteroids is in the main belt between Mars and Jupiter, through occasional perturbations through our planets, through gravitational interactions, a subset of them get knocked into our inner solar system. And that's where things get interesting for us in terms of potential close encounters with the Earth. So here you can see the Earth and you can see the neighborhood around it. Of course, the scales are not quite to scale, but you can see it's fairly busy around Earth. And so Gaia is helping us refine the orbits of these asteroids. And we're going to have a further release at the end of next year in which we will refine the orbits of these asteroids even further based on a longer range of data. Now, again, Gaia is another example of a mission which requires bringing together communities across essentially all of our member states. There is no one computer that can process all of Gaia data and produce all of the products that I've just shown you by itself. So it requires different processing units, which are distributed across our member states, and also require inputs from communities well beyond our member states. And so this is a very collaborative effort where they work closely with the European Space Agency in order to deliver the kind of spectacular results that I can only give you a preview about at the moment. And before I start to close up this talk, I wanted to, and start talking more about the community aspects, I wanted to also show you about a recent result that's absolutely spectacular. This goes back to the James Webb Space Telescope. And here what you're looking at is the furthest galaxy that has been imaged to date. And it's part of what we call a consortium. It's work that came out of a consortium based on an instrument that was provided by Europe to the James Webb Space Telescope. And so this, again, is a very collaborative effort between ESA, NASA, and our communities. And while the image alone doesn't allow us to confirm that this is a very high redshift galaxy, it's a redshift of 14, we actually required spectroscopic confirmation. So we need to actually look at the spectra of this object in order to confirm that it really is a high redshift galaxy and not some kind of interloper. And both the shape of the galaxy that's recovered, combined with the analysis of the spectra that have been obtained, which I'm going to show you shortly, essentially imply that luminous large galaxies were already in place 300 million years after the Big Bang. This is challenging some theories and certainly driving the modification of others. And so we are in an era in which new data are actually pushing theorists to advance our knowledge of the universe itself. And here is the spectrum that was taken that basically confirmed through what we call the Lyman alpha break that this indeed is a high redshift galaxy. And this was a very recent Nature paper. Just wrapping up the science part of the talk, we recently also released this beautiful full disk mosaic. So coming a bit closer to home from the furthest reaches of the universe and the earliest parts of the universe to our very own star, which is, of course, the sun. And we have a mission called Solar Orbiter, which recently completed its 5th year of operations. So it celebrated its 5th anniversary. And in order to celebrate that, the teams put together this gorgeous mosaic of the full disk of the sun. This is from actually the data we're taking in March 2023. It requires stitching together more than 25 individual sets of data together in order to produce these full disk images. Here you can see the brightness brightness image of the sun. So you can see material that's at a temperature of between 4,000 to 6,000 degrees. In this view, taken with the same instrument, but in a different mode, we can recover an image of the magnetic field of the sun at the same time. So red and blue regions indicate regions which have the strongest concentrations of magnetic field, and green and yellow have regions of weaker magnetic field. And you can see that the strongest concentrations overlap beautifully with where you have these dark sunspots, which is where we expect the strongest concentrations of magnetic field to be emerging from the solar interior. With the same instrument, you can also recover the velocity map, or what we call a tachogram, of the surface of the sun. And here you can see the line of sight velocity of the material in the sun, of the solar surface, with respect to the spacecraft, with respect to solar orbiter. And you can see that the blue regions essentially indicate regions that are coming towards us, red regions indicate regions that are going away from us. And so you can see that it traces the global rotation of the sun, which we know is a period of about 28 days. But you can also see substructure within that. So you can see these features, which are again concentrated around where we have the dark spots. And this is a very well-known disruption of the flow of material that happens due to the action of the strong magnetic field that's coming out. There's a lot more data coming from Solar Orbiter. The sun goes through an 11-year activity cycle. It recently passed its peak of activity last year. And so there will be many, many more results as the analysis of these gorgeous data sets are completed. And the final image I wanted to show you for Solar Orbiter, at least, is this heated image of the corona of the sun, heated up to a temperature of over 1 million degrees. And you can see that while a lot of the sun is peppered with heated material, you can see these concentrations of tangled loops that are particularly bright, and that's material that's been heated to over 1 million degrees. And this is information taken from data taken from the outermost atmosphere of the sun, called the corona. So these are regions overlaying the solar surface that I showed you earlier. And you can see very much where you have the hottest, most tangled loops actually correspond very well with where we had the dark spots in the strong magnetic field at the surface. Solar Orbiter itself, and this is common of many of our solar system missions, is composed of more than 10 instruments. Actually 10 instruments. It's a combination of instruments that do remote sensing, so they take pictures of the disk from a distance, as well as having what we call in situ instrumentation. So they measure the properties of material that the spacecraft itself is passing through. And again, this requires a collaboration of huge teams, not just for every single instrument itself, but for the entire spacecraft as a whole. And the individual instruments are led by teams from all across Europe, from Spain, Britain, Belgium, also the US and Switzerland, and France and Germany as well, to be complete. And so this again requires huge groups of scientists, technicians, engineers working together, problem solving, and then doing the data analysis. The science program overall is continuously populated through community consultation exercises. So here you can see quite a busy plot, but what it basically shows is a list of all of our missions going back chronologically from, so the oldest ones are down at the bottom. And of course, Hubble is in partnership, but it's led by NASA. And it goes back to 1990. And in green, you can see the missions that are still in operations. In blue, you can see the ones that have now entered archival phase or in legacy phase. And in purple, you can see the ones that are still to come. Now, this is a pipeline we have to keep populating, because if there are gaps, then that means that we stop serving scientific communities at the same level as we've been doing for the last 30 years. And so we conduct regular consultation exercises with the community. The first one, one of the earliest ones was in the 1980s, called Horizon 2000. It was followed up in the 90s with Horizon 2000 Plus, and it led to many seminal missions. I hope you've heard of some of them. We are currently working to complete Cosmic Vision, which is an exercise that started in 2000, but we're delivering it now. And this shows you the timeframes on which space missions are dreamt up, conceived, implemented, and then actually fully operated. And we're very fortunate in that the engineering is of such high quality that many of these missions are running well past what we would call their nominal lifetimes. We work on partner missions, of course. So there's HST, JWST, and SMILE. And SMILE is in partnership with China. And we also have smaller contributions to what we call missions of opportunity. Our latest consultation exercise was conducted a few years ago, and it's called Voyage 2050, out of which 3 large themes were identified to take forward. And these are areas that we're actively looking at. So moons of giant planets is a large, ambitious mission that we're working on defining right now. And once that progresses, then we will go into looking at the next big mission, which would be temperate exoplanets, sort of warm to exoplanets, planets around other stars, or looking at a follow-up to Gaia, depending on how that goes. And so these consultation exercises have to continue. At the same time, you run regular calls and announcements of opportunity, inviting the communities to submit their best ideas for what we call medium class missions. So those are missions that would cost sort of between 500 to 600 million euros, whereas L class missions are double that. And so we're going through that exercise right now, and we will be opening up a call later this year. Now, I just wanted to spend a little bit of time just talking about EDI and science missions. And one of the quotes, going back to Mary Jackson, that really resonated with me is that and she was speaking about students that she was working on getting interested in space science and STEM areas. I worry that not only are those students, but also we are not aware of the numbers of scientists from minoritized backgrounds. And it is very true that it's not clear how much we make career opportunities accessible and available to people going forward. And that's something that's always at the forefront of my mind as I look at the science teams that we work with and try to put actions in place to make these things as inclusive as possible. We recently had this image release in celebration of Solar Orbiter's 5-year anniversary. It was put together by one of the scientists working in our teams, inviting women working on Solar Orbiter to submit images of themselves. And this was in celebration also of the International Day of Women and Girls in Science. And here you can see a snapshot, a mosaic of scientists, engineers, administrators, all involved in making Solar Orbiter the massive success that it is today. And I think we have to keep highlighting these messages that there already are so many people from different backgrounds working on pulling together these missions and making them work. I'm a big believer that in EDI activities, you don't wait for wider change. You make change where you are and you enact it where you are. So we work on a local level on EDI activities and plug into wider efforts in the agency and beyond. And what we do within the working group that I lead is we share resources on relevant topics. We always try to educate ourselves. We make sure we have regular speakers coming in on different ranges of EDI topics. And we provide trainings to our staff and our fellows and our trainees to make sure they understand and they can build resilience as well, and as they build their careers. One thing I'm a big proponent of is codes of conduct for workshops and conferences, and that's something we have implemented for all of our scientific workshops and conferences that we sponsor and organize. And it's something that we always continuously look at in order to see if it needs to evolve further. Other areas that we're working on is looking at vacancy notices and seeing how we can make those more inclusive. We're very aware and we're starting conversations about areas related to neurodiversity because we're very aware that people have different needs and different ways of communicating with each other. One thing that we work very hard to do is connecting and enhancing efforts across the entire agency. So we work closely. ESA has a chief diversity officer. We work with local chapter groups across our various sites. There are early career scientist groups, there are women's groups that meet in different sites, and there are LGBTQI groups. And so we join together regularly and share notes and work at how we can uplift each other. And so these are efforts we're involved in. There's a lot of work to be done, and arguably too few people doing it, although I'm seeing more and more people engaging in these activities, which gives me a lot of hope. And certainly, I think all of us come in with ideas of the kind of environments we would like to have encountered when we enter these fields. And I think that's a good place to start. And certainly engaging with early career scientists and engineers is also another really important and powerful tactic. And so I will then conclude, and I'm open for any questions that you might have. Thank you so much for your time.
Thank you very much. Well, firstly, thank you. That was the most fantastic talk, and I have to say, I'm a lover of space as an aerospace engineer by background, and also have the commercial aspects of space in the contract side of things. But I've just been absolutely glued to my screen listening to you for the past half an hour. So thank you so much for providing such an insightful talk today. I've personally learned a huge amount. I'm sure colleagues on the call have as well. But really, really valuable conversation. So I know we're going to be looking at questions, as I say. Hopefully, if nobody else has, I've got an exceptional amount myself. But I think if you would like to call out to you, and we'll go through what that looks like. So the first question is, how does ESA's demographic profile compare with that of the general population? That's from Alexander Wood.
It's a really good question. I think there are gaps. I think there are certainly a big focus for a number of years has been looking at the gender balance because it's clearly off, especially the more scientific and technical areas that you look at. Partly it's a function of history as well, because people are hired into positions at a certain point of the time frame of the agency, and then you stay for the duration. And so people who are hired maybe not 50 years ago, we're just going through our 50th anniversary, but certainly 20 years ago would have been a particular demographic, and that is what's reflected in the population we have on staff today. It's changing. But what I also see and I worry about is that in our applications, we don't have the range of gender balance that I would like to see. So there does seem to be a bit of the mirroring effect that because people don't see people of certain backgrounds, they don't put themselves forward. And that applies across a range of different kind of parameters, right? So it's not just gender, it's also other minoritized areas. It's also in terms of people with disabilities and things like that. So we're conscious of it, but I do think we need to look at and learn more about how to get how to make sure people know that this is an environment for them, because I'm not sure we're doing that side of the equation as much as we could.
Thank you very much. And I think as a sector, we absolutely recognise it remains an ongoing challenge of getting the right balance of different characteristics in our workforce, for sure. So the next questions are coming in thick and fast now as well. What's the greatest challenges that bringing member states together on these various missions pose to you and your colleagues?
So there are a lot of challenges, but I mean, so the thing is, the good thing is everyone's extremely passionate. The hard part is that there are choices always to be made, right? We're building complex missions at every stage, actually. So in the building of the missions, there are compromises that have to be made because you have to fit within what we call programmatic constraints. So, budget, technical constraints, mass, all of these things, and that requires compromise. So we're always looking at, and that's something that I work on with the project scientists that work in my team, is it's kind of our job to push for maximizing the science, and it's the engineers' jobs to push back and say, yeah, no, this isn't going to work, right? And so we're constantly in a conversation with each other, and that naturally means that there's a certain amount of tension, and that tension, of course, translates to all of our groups as well that are involved. Different member states have different goals, they have different priorities, different technologies that they might want to bring into a mission, and that's a conversation that we're constantly working on with them, because we want Europe to build capacity. So we're always looking at, well, how can we encourage new players, as well as obviously delivering the amazing engineering that we have been for a number of years. So there's a lot of challenges, because also all of our missions are bespoke, right? Every new scientific mission that we do is designed to push the frontier of whatever topics or set of topics it's designed to do. And because of that, that means you're using new technology. It means you're pushing the envelope. It means you're trying to get the most bang for your buck, so to speak. And so that does require constant reinvention, to a certain point. It quite requires constant horizon scanning, working out where you are and what you can deliver. But I think when you were in operations, then the challenges are making sure the scientific community stay along for the ride, because of course universities, research institutes are always under pressure, and making sure that they're engaged and committed to the missions over the long term, over the long haul, is also a challenge we work on with the scientific communities, because obviously everyone wants to do great science, but making sure they can be resourced enough to do what the work that needs to be done is a constant battle.
Thank you so much. And the next question is from a colleague who said he didn't see the Parker Solar mission listed. Is this a NASA only probe?
It's certainly a NASA-only probe, but we coordinate observations with Parker Solar Probe. So we have some beautiful results that combine data that only Solar Orbiter could take, combined with Parker Solar Probe measurements. And they're really answering some really fundamental questions about, for instance, how the solar wind is propagated, and fundamental physics around that. So we work very closely together, not just with Parker Solar Probe. We work with the SDO, which is a ground-based observatory. We also work with SOHO, which is an ESA and NASA mission, but also other facilities. And we're talking, we're going to start also working with the Aditya satellite, which is led by India. Fantastic.
And then a more personal question on this note. So what inspired you to pursue a career in astronomy and physics?
So I always liked physics. I enjoyed it at school, and I loved reading science fiction. I think those two things helped. But then at school, I had a really great physics teacher, and I think that there were two things actually. So one was having an excellent physics teacher who really challenged us. And she kept telling us, well, okay, you have to learn this for your GCSEs, but actually it's a lot more complicated than that. So when you get to university, you're actually going to find out we don't really know, or it's much more complex. And that sparked something within me. But then also, I remember very early on when I was still at school, I got the chance in London to go to a Women in Physics event at UCL, and just seeing astronomers who are women really made a difference for me as well. It's like, oh, okay, maybe this is something, that I could build a career around. And I do think that just seeing somebody that you can somehow relate to does make a big difference.
100% agree with that. And a colleague has also asked, sort of tagging onto that, are there any specific routes into space science research from an undergraduate perspective?
So one thing that you can always do as an undergraduate, and I know I got the opportunity to do that too, is there's often summer projects and things. So if you can do a summer project, you can work out if you actually enjoy doing it, because I think that's one thing that's really worth establishing. Research isn't for everyone, right? And also, the other thing I would say is even if research isn't your bag, and it might be and it might not be. And for me, actually, what I discovered was that, at university, you get to do a final year project. And I discovered I loved my final year project way more than I loved exams. I hated exams. I can't tell you how much I hated university exams. And that just made me realize that, okay, maybe this is where the way my brain works. And it's something that works for me. It's something that motivates me. But the other thing I really want to emphasize is that in space science, we need everyone. It actually requires almost every kind of talent there is. So if you don't love physics, but you're good at chemistry, or you're interested in biology, or you're interested in ethics, all of these things are needed at the moment, particularly at the moment, in space science and in space generally. So I think if you're interested in this area, it's really worth trying to get experience, reaching out to people working in things that you think you might be interested in, and actually finding out what their day-to-day looks like. And then if you can get an internship or some experience, or get them to give you a project and see if that's something you like doing. I do think it's worth knowing if you like doing something, because sometimes you think you like something and you might not.
Fantastic advice. And I think, the practical element is absolutely key, isn't it? Because space looks incredibly exciting, but it's the reality of which part of it it fits for you. So one of the questions we've got left is asking about how has ground-based observatories been helping in your work?
They're critical, absolutely critical. So for Euclid, we needed ground-based spectroscopy to support preparatory work. We've got a mission coming up, which is called Plato, which is going to be looking for planets around solar type stars and around nearby solar type stars, so things that we can really characterize very well. And Plato needs a lot of ground-based time, like a lot of ground-based time, because it can get upper limits on, the sizes of what those planets might be, but without spectroscopy, which we can only get from the ground, we can't do much. So it's often critical. For the Gaia mission, for many years, we had ground-based observations, not just to complement the data that Gaia was taking, but even to track the satellite precisely and understand the movement of the satellite better. So ground-based observatories are actively helping, and where we can, we also try to involve amateur astronomers as well.
Fantastic. The next question is about ESA and how you work to be more efficient. So the question is, there's a lot of talk about companies and public bodies being more efficient. How does ESA accomplish such large projects and complex projects with many different organisations and different motivations? Is it efficient in its time and money? And how does it measure that efficiency to deliver its results?
So it's a good question. So we have we have metrics that we are held to by our member states, and we have to provide what we call key performance indicators to our member states. And part of those are the estimated cost plans, and how they evolve over time, and how they compare to the actual costs for each individual mission. Historically, there were some missions that went quite far beyond what the cost plans wanted. But recently we have models. There's a lot of risk. There's a lot of risk analysis involved, and a lot of mitigation around that's required. And also occasionally we have to go back and say, well, if we can't do something, then we really look at whether there's another way of approaching it. And we had that story. We had that case with an upcoming X-ray satellite called New Athena, which hasn't been adopted yet. But a few years ago, it turned out it was going to exceed the cost that it was planned quite considerably. And so we brought in expert committees to help us look at it again and say, okay, what is flagship science that can be delivered, but at much lower cost than that was coming in at the time. And that was a really successful exercise, and hopefully the rest of it will go smoothly. But every so often we do have to pull the brakes and say, actually, how can we bring this back into alignment? But it's always tricky, because there's always, you always want to do more, and so you always have to bring back and say, okay, we have to be responsible. This is taxpayer money. So you're always looking at, well, how do we make sure we stay within these bounds? And that's a continuous exercise, and we have pretty tough project controllers that keep us on track.
Very good. And building on that point as well, so another colleague has asked about how would you like members of the science and professional community to help make the case for space research in an uncertain world where there are many other calls, as you just said, on the public purse?
Absolutely. So I think one thing that's really important is that we're in a knowledge economy, right? We need a bigger STEM workforce, and Europe needs a bigger STEM workforce that is economically a good model going forward. And so if we want technologically literate people, space science is a really effective way to help build that. But also space science itself can help answer a lot of the technological and economic problems that we're having. So for instance, our Earth observation program, which is one of our sibling directorates, work very hard on ensuring that we have hygiened, credible data that people can benefit from in order to make decisions about disaster relief or agricultural planning or strategic planning, even of supply routes and things like that. So I think we're in a technological space now. I think also the rest of the world is catching up very quickly, or has even surpassed. And if Europe wants to be competitive, then this is a really important area to stay competitive in, and potentially very lucrative as well. So I think economically as well, the argument works. And it's better than making war. So science is an important tool for diplomacy as well. It allows scientists to talk to each other across many different divides and keep conversations going when sometimes other conversations have stopped. And that's probably important for humanity as well.
I agree. It's one of those domains, isn't it, where the collaborate and access piece is absolutely critical, and may have enduring partnerships regardless of, say, the geopolitical situation. So you mentioned earlier about ethics, and a colleague wants to understand, what is the role of ethics in space science?
So there's a lot to do with ethics. So there's a lot about our custodianship of low Earth orbit, for instance. So what are our responsibilities in maintaining low Earth orbit and cleaning up low Earth orbit, because there's already a lot of debris there. There is also the aspects of space safety. So what are the principles around when we go exploring? So when we have landers on Mars or Mercury even, but especially Mars, areas that have been identified as being potentially interesting in terms of understanding habitability. What are our responsibilities in terms of, contaminating that area, making sure it's safe biologically. And I think there's a lot of discussions around that, but there's also a lot of discussions around for instance, advertising in space, right? Is this something that people should be doing? Are there guidelines and guardrails set around what is and isn't acceptable? And I think those conversations need to be had. And speaking as somebody who's spent a lot of their career as a ground-based astronomer, I do know that, the constellations do cause us some pause, especially from the ground-based perspective. How many satellites and how many bright satellites would be too much? And what's the payoff, right? Because obviously they're also very important for communication, navigation, and all of those other aspects. So it's not saying, well, there shouldn't be any, but it's okay. So where are these rules? And the point is, it's a global effort, much like our oceans. It needs to be something that needs to be a global discussion and a global agreement, because it's the planets, not in individual countries or regions.
Thank you so much. And what I think might be our last question is bringing us back round to the start of the name lecture, back to NASA again, and a question around what do you think the demographic and diversity of ESA is and compared to NASA from your perspective?
It's interesting. I think very different regions, right, and very different definitions. So one thing that I found when I started working for the European Space Agency is we don't collect numbers very much. Whereas I know in the US, at least there used to be a much bigger emphasis on actually understanding what numbers were, and there were categories. Now with us, we have 23 member states, and so defining categories is actually fairly complex, because each of our member states have a different way of viewing what kind of demographics they would define and collect. And so it's a good question. I don't have a good answer to it. I do note that in the NASA astronaut classes, just very lazily, you can see that from the 70s, there were people of color in the astronaut corps, and the European Space Agency still has to get there. And so I would say that's certainly one for me, very stark, noticeable difference. But again, Europe is also a different space. And so it's conversations that we're having, but it's, I think it's quite different. But then, culturally, we're all going through different cycles in terms of these aspects. So I think it's something that we're continuously trying to navigate. And certainly I think my experience, because I grew up in the UK, obviously I studied in the UK, is our conversations on these aspects are much closer to the US, I find, than they are to some of the ESA member states. So it's interesting to me, but that's also part of diversity as well, right? So we have to navigate that too. And it's absolutely fascinating, because it's true that minoritized groups in different member states are different because of their histories. And so that's something that I think I would need to work with an anthropologist to understand a bit better, a sociologist to understand a bit better.
Thank you so much. So I think that brings us to the end of our questions. And I think a colleague was asking, are they recording the event today? Yes, we are. And that will be shared later on, so we can enjoy it all over again if we want to. On that note, I'm going to pass on to Cynthia, who's going to take us to the end of the session today.
Thank you so much.
Yes, thank you. And Gaitee, is that how you say your name?
Gaitee, thanks.
Gaitee.
Yeah.
I just have 2 words and 3 letters. Wow, amazing, and OMG to your talk. And I'm sure if Mary W. Jackson was here, she'd say the same thing. So I believe everyone online has been educated on the advances in space science research in Europe, your opportunities and your challenges. And I really appreciate how your presentation also described ESA's efforts tied to the Hubble and the James Webb Telescope. You know, I didn't know that. That was fantastic. I was geeking out when you were giving those those presentations and describing everything. So, and personally, I'm glad you showed how ESA is structured. You know, the 4 pillars. Because I work for NASA, and my center works with ESA developing the European Service Module, which we tested at our Neil Armstrong test facilities in Sandusky, Ohio. So that is the ESA piece or pillar I'm familiar with. So thank you for that incidental benefit, I'll call it. I also want to thank you for emphasizing the importance of creating a diverse workforce and ensuring those coming behind us see us in these STEM roles and positions, letting them know these STEM careers are achievable for them too. On a side note, I just want to give a quick shout out to Grant Locke, who's online. He's a grad student who I met. I believe he was a senior in high school. And Grant wants to do the same thing you're doing, and that is conveying what I call technical mumbo jumbo, scientific astronomical data so that Jane and Joe public can understand it. So I expect Grant will get back or get in touch with you soon. So lastly, just thank you, thank you, thank you. This was an excellent talk. And by the way, I'm with the American Institute of Aeronautics and Astronautical, or AIAA is what we call them. So I'm not royal. I wish I was, but so thank you.
Thank you so much. Thanks a lot.